Hello friends, we meet again. In our last discussion, we talked about the basics of combinational logic circuits. We learned that the two most popular transistors used in ICs are bipolar and MOSFET transistors. The high input impedance and input capacitance of the MOSFET transistors result in longer time constants for transistor switching speeds when compared with bipolar gates and therefore typically result in a slower device. We also discussed the characteristic parameters of TTL and CMOS family of ICs, where we learnt the noise margins, power dissipation, fan out, propagation delay, etc. In today's lecture, we shall have a detailed look at the TTL and CMOS subfamilies. The TTL series. The 74 TTL series has been the foundation and reference for virtually every new logic series of ICs. This series is easy to use and has excellent output drive capability. Was introduced in the year 1968 with a voltage supply of 4.5 to 5.5 volt. PD is equal to 10 milliwatt per gate. TPHL is equal to 8 nanoseconds. TPLH is equal to 13 nanoseconds. F maximum is equal to 35 megahertz. IH maximum is equal to 40 microampere at sink. IIL maximum is equal to minus 1.6 milliampere at source. IOH maximum is equal to minus 0.4 milliamperes at source and IOL maximum is equal to 16 milliamperes at sink. However, this series has high power consumption and is relatively slow, making the series obsolete when compared with the new TTL series. The 74S TTL series or the Schottky series has increased speed over the standard 74 TTL. It incorporates a Schottky diode across base to collector junctions of bipolar transistors within the IC. This reduces propagation delay by eliminating charge buildup at base region of transistors. It was introduced in the year 1974 with a voltage range of 4.5 to 5.5 volt. The other parameters, which include PD is equal to 20 milliwatt per gate, TPHL and TPLH are given. F maximum is equal to 125 megahertz. IH maximum is equal to 50 microampere. IIL maximum is equal to minus 2.0 milliampere. IOH maximum is equal to minus 1.0 milliampere at source and IOL maximum is equal to 20 milliamperes at sink. The 74 LS is a very popular TTL series used today. It has improved power dissipation over the 74S series, but isn't as fast and was introduced in the year 1976 and has a voltage supply of 4.5 to 5.5 volts with PD is equal to 2 milliwatt per gate and other parameters are shown here. The 74 ALS TTL series is a further improvement of the 74 LS series with less of propagation delay and power dissipation, thus rapidly replacing the 74 and 74 LS series. It was introduced in the year 1979 with the following parameters. The 74F TTL series is faster than the 74 ALS series. It also has improved noise margins, reduced input currents and better driving capabilities. It also handles heavier capacitive loads than earlier TTL families. It was introduced in 1983 with the following parameters. The CMOS series. The 4000 series is the original CMOS line. The 4000B series is an improvement. Supply voltage range from 3 to 18 volt with VIH equal to 2 by 3 VCC and VOH equal to 1 by 3 VCC. It was popular due to low power consumption when compared to TTL, considered obsolete when compared to the newer CMOS line of ICs, and is much slower than any of the TTL series. The 4000 series is also susceptible to damage from electrostatic discharge. It was introduced in year 1970 with a voltage supply of 3 to 18 volts with a PD equal to 1 milliwatt per gate at 1 megahertz, T PHL equal to 50 nanoseconds, T PLH equal to 65 nanoseconds, F maximum equal to 6 megahertz, IH maximum equal to 1 microampere at sink, IL maximum equal to minus 1 microampere at source, OH maximum equal to minus 3.0 milliamperes and IOL maximum equal to 3 milliamperes at sink. The 74HC CMOS series is an improvement in speed over the 4000 CMOS series, as speedy as the 74 LS TTL series depending on the operating frequency. It also provides greater noise immunity and greater voltage and temperature operating ranges than TTL. This is a very popular series used today and has the following parameters. It was introduced in the year 1975 with the following parameters. Like the 74HC CMOS series, the 74HCT CMOS series is an improvement in speed over the 4000 CMOS series. As speedy as the 74 LS TTL series, depending on the operating frequency, also provides greater noise immunity and greater voltage and temperature operating ranges than TTL. The only difference is that it is a TTL compatible to the level of pins and as well as input output voltage level compatible. Was introduced in the year 1975 with the following parameters. The 74 AC CMOS series was introduced in the year 1985. Its voltage supply ranges 3 to 5.5 volt with PD equal to 0.5 milliwatt per gate at 1 megahertz, and other parameters are shown here. So, we can say that it is a further improvement of the 74HC series. It's faster, has a higher output current drive capacity, and provides shorter propagation delays. The 74 ACT CMOS series was introduced in the year 1985 with the following parameters. 74 ACT is like the 74 AC CMOS series, that is, it's faster, has a higher output current drive capacity, and provides shorter propagation delays, but is TTL compatible, that is, it's pin compatible as well as input output voltage level compatible. The 74 AHC and the 74 AHCT are the advanced high speed CMOS and are enhanced versions of the 74 HC and the 74 HCT series. The 74 AHC has half the static power consumption, one-third the propagation delay. The 74 AHCT is TTL compatible, was introduced in 1996, has a voltage range of 2 to 6 volts. The 74 by CMOS series. The 74 by CMOS series of devices incorporates the best features of bipolar and CMOS technology together in one package. The overall effect is an extremely high speed, low power digital logic family. This product line is especially well suited for and is mostly limited to microprocessor bus interface logic. Each manufacturer uses a different suffix to identify its BiCMOS line. For example, Texas Instruments uses 74 BCT, while Signet's Philips uses 74 ABT. 74 low voltage series. This is a relatively new series of logic using a nominal supply voltage of 3.3 volt, which are designed for extremely low power and low voltage applications, example battery powered devices. Members of this series include the 74 LV, 74 LVC, the 74 LVT and the 74 ALVC. The switching speed of LV logic is extremely fast, ranging from about 9 nanosecond for LB series down to 2.1 nanosecond for ALVC. Another nice feature of LV logic is high output drive capability. The LVT, for example, can sync up to 64 milliampere and source up to 32 milliampere. Emitter coupled logic. Emitter coupled logic or ECL, a member of the bipolar family, is used for extremely high speed applications reaching a speed of up to 500 megahertz with propagation delays as low as 0.8 nanoseconds. There is one problem with ECL. It consumes a considerable amount of power when compared with the TTL and CMOS series. ECL is best suited for use in computer systems where power consumption is not as big an issue as speed. The trick to getting the bipolar transistor in an ECL device to respond so quickly is to never let the transistor saturate. Instead, the high and low levels are determined by which transistor in a differential amplifier is conducting more. Figure here shows the internal circuitry of an OR NOR ECL gate. The high and low logic level voltages and the supply voltage are somewhat unusual and cause problems when interfacing with TTL and CMOS. The OR NOR gate shown here is composed of a differential amplifier input stage and an output stage. In the differential amplifier stage, a reference voltage is set up at Q3's base via the voltage divider network. The reference voltage determines the threshold between high and low logic levels. When the base of Q3 is at a more positive potential with respect to the emitter of Q1 and Q2, Q3 conducts. The OR output goes low when Q5 conducts. If either input A or B is raised to minus 0.8 volt, that is high, the base of Q1 or Q2 will be at a higher potential than the base of Q3, and Q3 will cease conducting, forcing the OR output high. The overall effect of the ECL design prevents transistors from saturating, thereby eliminating charge buildup on the base of the transistor that limits switching speeds. Salient features of ECL. Different subfamilies of ECL logic include MECL 1, MECL 2, MECL 3, MECL 10K, MECL 10H and MECL 10E. There are many features possessed by MECL family devices other than their high speed characteristics that make them attractive for many high performance applications. The major ones are as follows. ECL family devices produce the true and complementary output of the intended function simultaneously at the output without the use of any external inverters. This in turn reduces package count, reduces power requirements and also minimizes problems arising out of time delays that would be caused by external inverters. The ECL gate structure inherently has high input impedance and low output impedance, which is very conducive to achieving large fan out and drive capability. ECL devices with open emitter outputs allow them to have transmission line drive capability. The outputs match any line impedance. Also, the absence of any pull down resistors saves power. ECL devices produce a near constant current drain on the power supply, which simplifies power supply design. On account of the differential amplifier design, ECL devices offer wide performance flexibility, which allows ECL circuits to be used both as linear and as digital circuits. Termination of unused inputs is easy. Resistors of approximately 50 kilo ohm allow unused inputs to remain unconnected. Logic gates with open collector outputs. Among the members of the TTL series, there exists a special class of logic gates that have open collector output stages instead of the traditional totem pole configuration. Within the CMOS family, there are similar devices that are said to have open drain output stages. These devices are not to be confused with the typical logic gates you have seen so far. Logic gates with open collector outputs have entirely different output characteristics. Figure here shows a NAND gate with open collector output. Notice that the Q3 transistor is missing in the OC NAND gate. By removing Q3, the output no longer goes high when A and B logic levels are set to 0 0, 0 1 or 1 0. Instead, the output floats when A and B logic levels are both high, that is 1, the output is grounded. This means that the OC gate can only sink current, it cannot source current. So, to get a high output level, use an external voltage source and a pull up resistor. Now, when the output floats, the pull up resistor connected to the external voltage source will pull the output to the same level as the external voltage source, which in this case is at 15 volt. Here you do not have to use plus 5 volt. One of the primary benefits of using OC gates is that you can drive load requiring voltage levels different from those of logic circuitry. Another important feature of OC gates is that their ability to sink large amounts of current. For example, the 7506 OC inverter buffer oblique driver IC is capable of sinking 40 milliamperes, which is 10 times the amount of current a standard 7404 inverter can sink. The ability of an OC gate to sink a fairly large current makes it useful for driving relays, motors, LED displays and other high current loads. So friends, here we come to the end of our discussion in this lecture and therefore we sum up. In this lecture we learnt about the various subfamilies of TTL and CMOS, learnt about their characteristics, their manufacture and the benefits of using one over the other. We also learnt about the ECL series and its features, and finally we discussed the logic gates with open collector outputs. So, that is it for today. See you in the next lecture. Thank you very much.